SwayamPrabha. Digital India. Educated India.
Hi friends, now we will start discussion on the second part of the module, characterization of wastes, and in this module we will concentrate on the determination of heating value of the solid wastes. So at first we will see what is heating value. If we combust some amount of waste, it will generate some amount of heat. So that heat can be used for different applications. So if we consider, say, one combustion chamber is there, we are putting some fuel, say solid waste maybe, so that is solid waste, we are combusting, oxygen is also sent. So after combustion heat is released. So heat is released and it is going through the flue gas. So that flue gas temperature we are reducing, say T1 here, so we are getting T2, we are putting some, say, coolant, so its temperature will rise, but this temperature will fall. Second, say another setup we are using, so coolant, and here we are getting T3. Now obviously T1 is greater than T2 is greater than T3, and ultimately that T3 will reach to TA, that is ambient temperature. So the amount of heat which are releasing, which we are getting from the flue gas after combustion, that will vary up to which extent we are considering the cooling of the flue gas. So here when the TA is the ambient temperature, when TA, that is temperature, is the ambient temperature, in that case we will get the maximum amount of heat for our further application. So that is called high heating value. So high heating value we get when the gas temperature is in ambient condition. Normally this is 15 degree centigrade. So another type of heating value is also there, that is called low heating value. So higher or lower, we can say higher and lower, somewhere sometimes higher and lower heating value also it is called. So that lower heating value will be lower than the higher heating value, and how much lower it will be? It will depend upon how much water has been produced during combustion, and that water molecules has captured some amount of heat for its vaporization. So the HHV is equal to LHV plus HV into number of H2O produced by number of fuels, number of moles of fuels. So if we take n number of fuels, n number of moles of fuels, then n H2O out, number of moles of H2O produced during combustion divided by number of fuels into heating value for the vaporization of water. So this amount of heat if we add with the LHV, that will be the HHV or high heating value. So this is the relationship between high heating value and low heating value. Now how can we determine the heating value? The Bohm calorimeter is normally used to determine experimentally the heating value of any solid and liquid samples, or maybe waste also. So in this case, as shown in the figure, so this is our Bohm calorimeter. So this is our Bohm. So in the Bohm, some amount of solid waste can be put in this crucible, and after putting the crucible inside the Bohm, the ring attachment will help to tighten it, and then oxygen will be passed through some nozzles and high purity oxygen will be provided into the bomb, so that it will ensure the complete combustion of the solid waste or any liquid waste also are put here. So, the basic principle of this bomb calorimeter is that the amount of heat which is being released by the material here inside the bomb, that will be transmitted through this wall and will raise the temperature of the water kept in the water bucket. So, ultimately temperature will rise, but this temperature rise should be say 2, 3, 4, 5 degree centigrade like this. So, amount of materials will be selected in that way, and normally it is around 1 gram, not much more amount of solid or liquid waste is added here. So, then on equilibrium temperature will rise, then that after at that time what is the difference in temperature initial and final, that will be the temperature rise. So, mCp dt will be the total amount of heat released by the solid present in it. So, this is the mechanism, the heat released by the solid or liquid waste is captured by the bomb as well as the water inside the bucket, and the temperature rise is measured. So, mCp del T, that the amount of heat received by the water and the bomb is equal to amount of heat released by the solid materials or liquid materials in the bomb. So, now what is the operating procedure? So, we have to take 1 to 1.5 gram of materials that is charged in the bomb, and the bomb is highly pressurized with pure oxygen. Then when we are putting inside it, after fixing this one by ring attachment, we will supply oxygen. Then it will put inside this one and that will be inside this container. Then we will ignite the material through this electric circuit. There will be some wire will be used, fuse wire will be used and or threads, and then that this is the temperature measurement instrument, some thermocouple will be here, water bucket, and the temperature measurement will be done. So, these are the steps, but when the equilibrium temperature will reach, we will reach the equilibrium temperature, then our run is almost complete, then we will release the pressure inside it, then we will open it and we will find if there is anything inside the bomb or if there is any material unconverted. If it is unconverted, the test is discarded. So, thereafter we will collect the fused wires if any, then we will straighten it and we will get the length of the wire present, and we will get the subtraction between 10 centimeter minus the total length of the wire we are getting at the end. So, that will be used to determine how much of energy the wires has generated during the combustion method. So, during combustion, if there is sulfur and nitrogen, some acid will form. So, acid will be deposited on the surface of it when the condensation will take place. So, that has to be collected, the washing liquid has to be collected and titrated against sodium hydroxide or calcium hydroxide or any other alkali solution, standard solution, for the correction of those acid, sulfur and nitrogen correction, and another correction will be thread correction, that is used for ignition. So, these are the corrections required and these are the procedure. Now, I will show you some video, it will explain, it is self explanatory and it will explain how this work. So, the material is taken, this is the crucible, the material is taken and it is put inside the bomb. And now it is tightened. So, oxygen is sent through this nozzle into the bomb. So, pure oxygen is supplied. You see the pressure here, the pressure is increasing inside the bomb, the oxygen pressure is increasing. So, now oxygen supply line is opened. So, this is a bucket with water, that is 2 liter of water is normally added. So, water are added. So, this is inside this bucket and water is added. Now, bomb is put in the bucket. Then the electric circuit is getting ready. Now, we will cover the lid. The covering is being done, the container is being covered by the lid. Now, this is the thermocouple. So, that is inserted into the water present in the bucket. Now, it is going to be ready for firing. So, now it is running. So, firing will start now. So, set 0, that is initial point. So, set 0, okay, then it is firing, fire starts. we see the temperature will increase. That is increasing 0.29, 0.68, 0.683 degrees centigrade. This is the differential temperature. So, this will continue until we reach the equilibrium temperature. Okay. So, now we have reached the equilibrium temperature and the procedure is like this, just explained, as well as the video is shown to you for better understanding. Now, after that we have got some information and some values. What are those? The initial temperature, final temperature, and then we have, after this test, when we will be taking the washing of the bomb, so that wash will be titrated and we will get the amount of tighter liquid required, that is standard sodium hydroxide or potassium oxide or any other alkali required for its neutralization. So, that will be C1 milliliters of standard alkali solution required, and then we will get C2 percentage of sulfur in sample, that is known to us if we have some CH analysis of the solid waste or any other liquid waste also. So, C3 is the centimeters of fused air that was used or consumed in firing. So, that we can determine, and mass of sample how much we had taken, that is known to us. So, these are the parameters, now it is known to us. Then what is the principle? Heat released by waste sample is equal to heat received by bomb and water, bomb and water in the bucket. So, how can we measure? This is equal to mCp dt mass Cp into del T. Del T can be measured, that is Tf minus Ta, final temperature minus initial temperature, we can measure that T equal to, that is del T, T equal to Tf minus Ta. And then what is our Cp, mCp? Say we have m1 of the bomb, m of the bomb into Cp of the bomb, mCp into del T plus m of the water in the bucket, Cp of the water in the bucket into del T, that is equal to del H, which is received by the bomb and the water in the bucket. So, that is equal to, we can write mBCp B plus mW CPW into del T. So, this is equal to say W del T equal to del H. So, this is the relationship which is used. So, this W is water equivalent. So, that is called water equivalent of this. So, our first job for determining the heating value, to determine the water equivalent of the bomb calorimeter, and that is done by using certain amount of material, the del H value or the heating value of that is known to us. Benzoic acid is used basically. So, in this case benzoic acid is used. So, this is our case, we can get the value of W. So, once we get the value of W, then heat released by the solids equal to how much? H into M. M is the mass of the material we have taken and H is the heat released per unit mass. So, H into M, that is equal to W into del T. So, this is the relationship which can be used to determine the heating value of the material. Now, the W del T which we are getting, that requires some correction, that is the total amount of heat which is received by the water and the bomb calorimeter, but all that amount of heat is not actually released by the materials. Some amount of heat has been contributed due to the formation of acid like say HNO3 and H2SO4, due to the presence of nitrogen and due to the presence of sulfur, and some amount of heat has been contributed by the fused air. So, we need to get the correction of E1, E2, E3. So, ultimately we can calculate Hg, say here H is equal to W into del T, here we are mentioning T, minus some correction. What are those? E1 minus E2 minus E3 by M. So, this is the relationship for determination of H, that H is high heating value, higher heating value or gross heating value. So, gross heating value can be determined by this formula. So, now we have to determine E1, E2 and E3 values, and E1, E2, E3 values can be determined from the value of C1, C2 and C3, when C1 is the amount of ml of standard alkali solution required for the neutralization of the bomb wash, and E2 can be determined from this 13.7 into C2 into M, where C2 is the percentage of sulfur and M is the mass of the solids or the samples taken into the bomb, and E3 can be calculated depending upon the nature of the air which have been used. So, different types of airs it is given and different relationship has been given. Obviously, the amount or the length in centimeter of the air fused during firing, that is responsible for determining the E3 value as per different equations it is given here. So, we can get the Hg value by using this formula. Then what will be the W determination? How can we determine the W? So, for determination of the W, similar test we will do. In that case, the heating value of the material is known to us. In that case, for example, say here benzoic acid is used. So, a pellet of benzoic acid not less than 0.9 or not higher than 1.25 gram is used, and in that case what we will get? W is equal to H into M plus E1 plus E3 by T. So, same formula if we like this. So, Hg into M plus E1 plus E2 plus E3 divided by T divided by T. So, this T means del T. So, this T means del T. So, this is the formula by which we can get the value of W. But now in benzoic acid the material is known to us, there is no sulfur. So, this component is equal to 0. So, ultimately we are getting the formula W is equal to H into M E1 plus E3 by T. Now, H is known for benzoic acid, M is known, that how much we have taken, E1 E3 is known and T is known. So, W can be calculated. Now, what will be the net calorific value? So, to determine the net calorific value, some empirical relationships are given, that is H net is equal to 1.8 into H gross higher heating value minus 91.23 into H, where H is the hydrogen percentage, but this is when Hn in unit of BTU per pound, but after conversion we get 0.555927 into 1.8 Hg minus 91.23 H in kilocalorie per kg unit, and some other expressions are also available, that HHV and LHV are related on the basis of hydrogen, oxygen and moisture content, hydrogen, oxygen and moisture content in the feedstocks, because all those three, the hydrogen produces H2O, oxygen produces H2O. So, that amount of H2O produced during combustion is responsible for the lower heating value. So, that is why this relationship is also used. Here we will see some empirical relationship proposed by different researchers for the determination of high heating value based on proximate analysis, based on ultimate analysis, etc. Now we will see one example. A solid waste with 1% sulfur is combusted in a bomb calorimeter. The temperature of the bucket water increases from 25 degree centigrade to 28 degree centigrade. The water equivalent of the calorimeter is 2402 calorie per degree centigrade. 1 gram sample is used for the test and par 45C10 wire is used for ignition. Out of the 10 centimeter wire, 2.6 centimeter is unused. The titrate to titrate the calorimeter washing 24.2 ml of 0.0709 N sodium carbonate is required. Calculate the gross heating value of the waste. Consider the thermometers are working perfectly. So, there is no need for thermometer correction. So, we are using it is a perfect working. So, how to calculate the high heating value? We know the formula Hg is equal to W into T minus E1 minus E2 minus E3 by M. So, in this case we can calculate E1. What is E1? For calculating E1 we need C1. C1 is equal to how much? 24.2 ml of standard sodium carbonate. So, 22.4 into 1, that is E1 is equal to 24.2 calorie. For E2 it is required sulfur content. So, 1% sulfur. So, E2 is equal to 13.7 into 1 into mass of it 1 gram. So, that is equal to 13.7 calorie, and for the determination of E3 we need how much wire has been consumed. So, out of 10 centimeter 2.6 centimeter is remaining. So, consumed is equal to 7.4 centimeter. So, as the type is par 45 C10, so 2.3 into 7.4 that is equal to 17.0 calorie, that is the E3. So, now we will put the value of E1, E2, E3. W is given 2402 calorie per degree centigrade, T is equal to 28 minus 25, that is equal to 3. So, 3 into 2402 minus 24.2 minus 13.7 minus 17 divided by M, M is equal to 1 gram. So, we put it here and we are getting 7150 calorie per gram. So, this is the high heating value of the material. So, up to this in this module, and in this module we have discussed how to measure the heating value of any solid or liquid waste. So, up to this in this module, thank you very much for your patience.